So we're going to finish up chapter 4 today. I didn't post a discussion question. Meant to, didn't get around to it. So if you have any questions on the chapter and the review, we'll fill those kind of at the end of the lecture. So posted a recording on Friday and got through most of the rest of the chapter, but just to kind of review what it was that the recording was over. Talked about the charges, electric charges in motion create a magnetic field, and the charges that we're interested in electricity is the electron. And so, the positive charges are inside the nucleus of the atom, and we don't utilize those for electricity except for we send the electrons down the wire. So all discussion about electricity and magnetism as it relates to electricity is all around the electron itself. So talked about the similarities between electrostatics and electrodynamics and magnetism. And we get a flow of electricity through a wire, we create a magnetic field, and we can use that wire and we can manipulate that wire in order to intensify the magnetic field. So we take that coil wire, or that wire, and we coil it up. And essentially what it becomes is like joining magnets together. So before I do that, we talked about the similarities again between the laws of electricity and electrodynamics and the laws of magnetism. They were very similar, and that was that if we have we want to make a stronger magnet, or the strength of the magnet is equivalent to basically the magnetic dipoles. So the more magnetic dipoles that we have, the stronger the pole strength of the magnet. Basically the same as the more electricity we have, the more electricity we have. The laws of electrodynamics, electrostatics, where essentially the more electrons you have, the more electrostatic charge you have. The same thing applies to magnetism, and that is that the more magnetic dipoles you have, the stronger the magnet you have. So you got that, and then you've got, and it's inversely proportional to the square of the distance between them, which is the inverse square law. So if we take our magnetic field, or our wire, and we coil it up, then essentially what we can do is take the magnetic field that's around each one of those wires, because again, our magnetic field orients perpendicular to the wire, so it's reaching out in all directions. So if we coil it up, essentially what we can do is take the individual magnetic fields around each one of those wires and join them together to create a bigger, strong magnet. And we'll talk more about that here in a bit. So we talked about similarities there. Obviously, we talked about the history of magnetism. Talked about the magnetic field lines reaching out from the magnet itself indefinitely, right? So we said that the smallest unit of magnetism doesn't exist, right? Because if you have the magnetic field that comes off of the smallest magnet being one single atom that shows a magnetic property, and any atom that has unpaired electrons shows a magnetic property, that would be basically one magnetic dipole, right? So one magnetic dipole is the smallest magnet, but the magnetic field reaching out from that magnetic dipole reaches out indefinitely. So there is no single unit or smallest unit of magnetism. It doesn't exist. It extends forever. So then we talked about the different types of material and their relationship to magnetic fields. And I said that there was basically 4. There were materials that completely ignore the magnetic field, and those are what we call non-magnetic. And I talked about the things that are slightly repulsed by magnetic fields, and those would be things that are diamagnetic. You really can't observe that. Then we talked about things that are paramagnetic. And paramagnetic would be things that are weakly attracted, and you really can't observe that either unless you've got extremely strong magnetic fields. And I related a story about the MRI magnet. If you haven't seen the video from Friday, and I know a lot of people haven't looked at the analytics, then you know is going completely over your head. But paramagnetic material is weakly attracted, so that things that we tend to think of as being non-magnetic are truly magnetic. It's just that they're so weakly attracted that you can't observe it unless you have an extremely powerful magnetic field. Aluminum being an example. And then ferromagnetic materials or anything that are strongly attracted, and that would be things like iron. So iron is where we're going to live for the rest of the day-to-day for the most part when we're talking about magnetic fields and electromagnetism. So then we talked about how we learn that electricity is created with moving charge, and that was by accidental discovery, or as I guess maybe it was an accidental discovery, where Galvani had materials that were of dissimilar type, metals of dissimilar type, and if you have metals of dissimilar type, sometimes you get a electric charge out of it. And he had these things hooked to a circuit, and the circuit accidentally touched a frog leg twitched, and we realized two things at that point, and that was that nerves work off of electric impulses, and dissimilar metals create an electric current. So Alessandro Volta came behind him and created the first battery, and that first battery was called a voltaic tile, and it's just stacks of dissimilar metal to create enough of a charge that we can actually use it. So that's the first battery, is voltaic tile. And a battery is just a source of electromotive force. So it's a electromotive force being voltage, pushing amperage. So first battery. We don't use that anymore. We use something totally different. So then along came Oersted, and Oersted is the person who actually proved that a moving charge creates a magnetic field. And he was the guy that had the circuit with the compass, and whenever he connected it to the battery, the compass wouldn't point it north, it would point at the circuit. And along came Michael Faraday, and he questioned whether or not you can make, since you could make magnetic field with electricity, he questioned whether or not you could make electricity with magnetic field, and it turned out you could. But there had to be four things present. You had to accomplish four things to make that happen. Well, really you only had to have one thing, and that was a changing magnetic field. We'll talk more about that here in a bit. But he also found that the amount of electricity that you created was dependent on four things, and those were the four things that you see on page 78. Magnitude of the induced current depends on the strength of the magnetic field. So the stronger the magnet, the more electricity you can create. The velocity of the magnet as it moves past the conductor. So you had to have a changing magnetic field. The influence of the magnetic field had to change in relationship to the wire. All right. So the faster you moved it, the more electricity you create. The angle of the conductor to the magnetic field, and then finally the number of turns upon the conductor. So a flat wire created electricity, just not a whole lot, or created electricity, just not a whole lot. So if we doubled it up, we pulled it up, then we create more. So that was Faraday's contribution. So what we're going to do today, and I talked about electromechanical devices, really anything that you put into the circuit that uses the electricity or manipulates it anyway is electromechanical device. Specifically in the circuit, what I talked about was the turning of the rotor. All right, so electromechanical devices either create electricity or they with mechanical energy, or they create mechanical energy with electricity. All right, so that brings us up to today, and what we're going to talk about today is we're going to go back through some of this, and we're going to refine some of this and talk about how we got to where we are using this stuff. And also, we're going to talk about the transformer. We're going to look at transformer laws. We're going to look at how we manipulate voltage so that we can create the X-rays in the energy that we want them to be in. So, moving charge creates magnetic field, right? So magnetic field can create, in turn, electricity. There you go. So it depends on a number of different things. All right, so first off, if I have a magnet, and this is representative of a bar magnet, most of the time your magnet's going to be made out of ferromagnetic material. It's got to be made out of ferromagnetic material, or a combination of things that become ferromagnetic. So in a magnet, we talked about magnetic induction. Magnetic induction is just induction of or creation of magnetic fields through something that's ferromagnetic. So I have a magnet here. It's got a north and south pole, and the magnetic field stretches out from one end into the next, and I take a piece of iron and I get it close enough to it, then these magnetic field lines will distort and go through that ferromagnetic piece of material and eventually draw it all the way in until the two are touching. And what happens is the magnetic field intensifies through both, piece of ferromagnetic material wasn't that big, through both of these, and they both become magnetic. So what I've done is I've induced a magnetic field inside of that piece of ferromagnetic material. So basically what I've got is a bigger magnet. Now, the bar magnet, if this was a bar magnet, the way the magnetic fields orient, or how the individual magnetic dipoles orient, is along an axis that would go with magnetic field. Okay, so if you've got some things in here that are pointing in different directions, they're going to have a tendency, even if this particular atom is not necessarily aligned with the magnetic field, because it's in the magnetic field, it's going to have a tendency to align with it. All right? So where we run into a little bit of a problem is copper is, I don't know where it falls on the spectrum of diamagnetic versus ferromagnetic versus paramagnetic. It doesn't really matter. It's just not as magnetic as iron, okay? Which means that when I send electrons through it, so I've got electrons going through it, I've got a charge in motion. So I've got a charge in motion. What do I create? Magnetic field, right? So I got a magnetic field. So even though this coil of wire, which is probably copper, maybe aluminum we said was paramagnetic, it's not going to be as susceptible to magnetic fields as that piece of iron, ferromagnetic piece of material, right? So our individual dipoles are not going to have tendency to align like they did inside the magnet or inside the ferromagnetic material. So what happens is if I've just got a straight piece of wire, then again, we're looking straight down onto the piece of wire. The orientation of the magnetic field is pointing out in all directions. We do have a north pole and a south pole on the coil wire. It doesn't really matter, but where it is, it's just that the magnetic field is all the way around it. All right, so we've got all these magnetic dipole equivalents because we've got electrons running through it. But what we've got is magnetic fields that are just going around and around and around and around the wire, okay? So they're not lining up as well as what they would in a piece of ferromagnetic material or a bar magnet. They're lining up, but they're not lining up as well. If I put these things close enough together, then they're going to overlap, okay? So these things are kind of spinning around doing their own thing, but if I put them close enough together, then those magnetic fields will overlap and this whole thing will become magnetic, like a single big magnet. But still, what I've got are currents, basically magnetic currents that are spinning around these individual pieces of wire. So even though by bunching them together and bringing them closer together, because the further I spread them out, the magnetic field weakens according to the inverse square law. If I mash them together, it strengthens, right? So if I mash them together, it strengthens, but they're still going around and around the wire. So it's not as efficient as just a big chunk of iron, because we're going to lose some of the magnetic field as they spin around that. It's still, because of the four laws of that Faraday established, wrote, we can, depending on how much current we run through that wire, we can still make a magnet and a magnetic field that's far more effective than this one. It's not as efficient, right? Because we're going to lose some magnetism, but it's much stronger. We can create an extremely strong magnetic field by pulling wire. And what we have there is what we call a solenoid. A solenoid is basically an electromagnetic device that is sole reason for existence is to create a magnetic field strong enough to accomplish something. And you use these all the time. Every time you unlock your table, you step on the little pedal, you hear a clunk, right? And what you're actually doing is you're energizing a solenoid to run a current of wire through, or a current of electricity through a wire to create a very, very strong magnetic field. That magnetic field releases a brake. Every time you hit the locks on your tower, you're doing the same thing. So on your tower, what you've got essentially is you got rails up into the ceiling, and then you've got these rollers that your tower rolls on. And the same thing happens when you extend either up or down your tower. But it's rolling on these rollers, and it's got a brake that mashes into the rail. So right below that brake, what you've got is a solenoid, so that when you mash and you want to take your tower somewhere else into the room, you mash those, the buttons, and what that does is it energizes this to release this lock so that the brakes are no longer on and you can drag that thing around the room and put it anywhere that you want it to be. Okay, so a solenoid is just a coil of wire with electricity running through it to create a magnetic field so you can do some work. That's all it is. But a solenoid, again, we can, because we're using electricity supplied from the power company to create this magnetic field, we can make it very, very powerful in a couple of different ways, and primarily in one way. And that is, going back to Faraday's laws, the magnitude, well, this depends on the induced current, but it really applies also to the amount of magnetism that we're going to create. The more of a, the more current that we push through a wire, the more magnetism we're going to create. Okay? So, the current coming into the hospital is running about 110 to 120 volts. Some cases it may be 220 to 240 volts. So we got relatively high voltage, and we can send as many electrons in amps, because amperage is the flow of electrons, as many electrons down this thing as we want to. So the more electrons we send through it, the more magnetic field that we can create. Have you ever been in a hospital when they did a fire, the fire alarms went off? Yeah. Okay, before the fire alarms go off, what you'll see is the doors typically stand open, right? And the fire alarms go off and the doors shut. And the reason the doors shut all by themselves is because on the wall, what you've got is this thing that holds onto the door, and that it's basically an electromagnet. It's a solenoid. And it's a very strong magnetic field, so that if you just walk up to the door and try to shut it by hand, sometimes it won't shut, because some of the doors in the hospital, by regulation, need to stay open unless there's a fire. And once a fire alarms go off, they turn off the electricity to those solenoids and then close all by themselves. So some of those things, you can't make them close. You can pull on them all day long, and the magnetic field is so strong that you can't pull the doors away from the solenoid. But if they kill electricity to it, you have no more flow of electrons going through the solenoid, then what happens to the magnetic field?
What's it?
It goes away. It's gone, right? So a solenoid is just basically, again, it's a coil wire that is used to create magnetic field that we can use in some way. You can further improve the magnetic field by putting a piece of ferromagnetic material in the middle of it. All right, so what would be the significance of putting a piece of ferromagnetic material in the middle of a solenoid?
You want it to be strong?
You want it to be strong, right? So you got magnetic induction, right? But with the solenoid itself, without any kind of core to it, and this is what we're going to call a core, this ferromagnetic core, then what I've done is I've taken a piece of iron or some sort of ferromagnetic material and I put it into the middle of it. And what I had before were some of these wasted magnetic fields spinning around each individual wire. Most of the magnetic field was going to join up together and make a bigger, stronger magnet, but you lost some as it spun around the wire. By putting the ferromagnetic core into the middle of it, some of those spinny little magnetic fields are going to join together, and now you've got a more efficient magnet. So really fundamentally, a solenoid and an electromagnet are the same thing. We're just going to say electromagnet is a solenoid with an iron core, all right? But really the same thing, fundamentally. They do the same thing. It's just that in one case, we've got an iron core that helps to direct those wayward, lost magnetic fields, makes them join up, and improves the efficiency a little bit more. Okay? Now, what that also is an illustration of your auto transformer. So electricity comes into the hospital, it comes into the imaging suite, and the first thing it gets to is your
Room.
what's that? Your room, yeah. Yeah, but in your imaging system, the first thing it hits is I just said it a second ago, auto transformer. Well, it's solenoid, kind of. It's auto transformer. So you got auto transformer. Auto transformer, what's the purpose for the auto transformer?
Transforming the electricity.
Transforming the electricity. Specifically, what are we doing with it? Oh, how quickly you forget. What's the purpose for the auto transformer?
Increase and decrease voltage.
Bingo, it's our KVP selector. Do we have KVP at this point? No, we don't. We're just going to say, for simplicity's sake, that we feed it 100 volts. We don't have electricity at this point. The contacts on the primary side are set, and your auto transformer is nothing but an electromagnet, really, because it's got an iron core in it. So what we have is two sides to it. We've got a primary side and we've got a secondary side. Now, if we supply electrons to this, what do we create? We send electrons through it. Electricity goes through the coil wire. What do we create?
Electromagnetism.
We create magnetism. We take electricity and we create magnetism. So how do magnetic field lines orient?
One end to the other?
One end to the other, exactly. So they go out of one end and into the other. So now, if we come along and on our secondary side, we plug into a different place on the secondary side. First off, if we plug into the exact same place on the secondary side, then the voltage on the secondary side is going to be identical to the voltage on the primary side. So we have 100 volts in, we're going to have 100 volts out, right? So if we spread them out, then I have more turns on the secondary side than I have on the primary side. The primary side is the side that I supply with alternating current. As it goes in, it comes out, and it goes in, it comes out. So secondary side, if I spread them out on the secondary side, then our 100 volts goes up or goes down?
Up,
Goes up, right. If I bring them together, then our voltage goes
down.
down, right. So we're just gonna say goes up. So after it comes out of that, what does it go into? So I've still got, well, let's say I've got 110 volts now. What does it go into after it comes out of the auto transformer? Auto transformer is a rheostat, turns up, turns down, the magnitude of the voltage on the secondary side, based on the turns ratio. Where does it go after this? High voltage transformer, exactly. So high voltage transformer, based on what we just saw here, if I have more turns on the secondary side of something than what I have on the primary side, then what happens to our voltage? Got more turns on the secondary side than the primary side, it goes up. It goes up, right. So what I'm gonna have, because what I want is high voltage, I'm gonna have more turns on the secondary side than what I'm gonna have on the primary side. Now, here's where this stuff matters. It's hard to see it here, but it's a little bit easier to see it here. Right? So these are basically the same thing as this. They got an iron core in it to increase the effectiveness of the magnetic field. Now, if I send electricity through this coil wire, what do I create? Come on, we just did this here. Magnetic field. I create a magnetic field. So I send electricity through this coil wire, I create a magnetic field. Now, if I put another coil wire close enough to it, and let's say I'm not working off of alternating current, let's say this came out of a battery is a source of direct current, it only goes in one direction. So I've got a moving charge here, so do I have a magnetic field? Yeah, I do. If I move this coil over, or let's say I don't even move it, it's already there when I apply the direct current to it. What do I create over here? Do I create anything over there? Okay, Faraday proved what? Oersted proved that you can create magnetism with a moving charge. Faraday proved that you can create electricity with magnetism, but the magnetism has to do what? It has to change, it has to move, right? So, this direct current, we create a magnet, does that magnetic field change with the direct current just going through it at a consistent rate?
No.
No, it does not. So with direct current, do I get anything over here?
No.
No, I don't. So, this is why all this matters, is what I have to do is I have to supply alternating current to this. Okay, so alternating current does this. It goes in and it comes out, and it goes in and it comes out, and it goes in and it comes out. Okay, so electricity goes in one direction and then it turns around and it goes in the opposite direction. Now, what happens in doing that is that, let's say, as the electricity is going in that direction, so it goes in and it comes out up here, it goes in and comes out up there. Let's say that makes the north end at the top and the south end at the bottom. Okay? So, how are our magnetic field lines oriented? Well, I had a question on Monday about the illustration on page 75, and I think that I described the magnetic field coming in one end and out the other, and then I changed during the lecture to where it switched around. And that doesn't matter. I'm not going to ask you which end of the magnet that the magnetic field lines enter and which end they exit. Doesn't matter. It doesn't matter. What you need to know is that they do enter one end and out the other. So for this illustration, what we're going to say is the magnetic field lines enter the north end. Okay? They enter the north end and they exit the south end, like that. So they go all the way around when current's going that way. But when current reverses, it comes back and it goes that way, and it reverses and goes that way, then what's going to happen is that our magnetic poles switch. So north is there and south is here, and our magnetic field lines now enter here, and they exit there. Did my magnetic field change? No? No? Okay. So if this is a bar magnet, and I've got bar magnet sitting right here, and this is north, and this is south, and I take my bar magnet and I go zip. Did it change?
Yes.
Yeah, it did. So in giving it alternating current, does my magnetic field change? Yes, it does. Not only does it change, but it changes very rapidly. Okay, electricity, this happens in the US at 60 hertz. Well, what's a hertz? That's 60 times per second. How fast is that?
Really fast.
Really freaking fast, right? So, back to Lenz's law, or to Faraday's law. The magnetic, or the magnitude of the induced current depends on the strength of the magnetic field. Okay, so stop there. Strength of the magnetic field. How do we make magnetic field stronger? Send more electrons to it, right? So we got almost an unlimited supply of electrons. Number two is what? What does it say? Base 78.
The second one?
Yeah,
The velocity of the magnet field as it moves past the conductor.
right. So velocity means what?
Speed.
Speed. So again, I'm back to flipping my magnet. I got a bar magnet. If I could turn this thing 60 times in a second, how fast would that be? It'd be pretty quick, right? So if I can flip these magnetic poles 60 times a second, is that pretty quick? Yes. So can I use alternating current to flip my magnetic field 60 times a second and induce a much greater electromagnetic force on the secondary side over here?
Yes.
Yes, absolutely. But it has to be changing. That's why we have to have alternating current, is because that gives us a fluctuation. It's in constant flux. Our magnetic field is in constant flux, so that as we move a secondary pole closer to it, I can induce a magnetic field on the secondary side. And number three, whatever. Number four, though, what does number four say? Number of turns. So what did I do between the primary side and the secondary side? Increase the number of turns. So that what I get is, if I feed this thing 100 volts, what I'm going to get on the other side is maybe 100,000 volts. So what you get whenever you step up, you use the step-up transformer, what you get is a change in the magnitude of the voltage on the secondary side on the order of maybe 1,000 times higher than what you have on the primary side. So it takes the voltage and it increases it to a ridiculous amount. And that's a ridiculous amount we need, because let's say we change this to 110 volts, and let's say we'll work through the math here in a bit, but if we feed it 110 volts and we have a turns ratio of 1 to 1,000, what that means is that I'm going to have 1,000 times the amount of voltage on the secondary side. So my 110 volts becomes 110,000 volts. Okay? So what is 110,000 volts? That's 111, 110 kVp. So what are you doing now? So first exam you learn. Chest X-rays, right? Okay. So what we do is we take alternating current, has to be alternating current, or this doesn't work. because we have to use a changing magnetic field on the primary side to create an induced current on the secondary side, so we can feed that induced current into the primary side, the step-up transformer, to create an induced current on the secondary side of the step-up transformer. Okay? Now the trick here is that as voltage increases, amperage decreases by the same amount. So, okay, you've got some good amperage going into this thing. You got, I don't know, maybe 10 amps going into it. But if our voltage increased by 1,000 times, what's our amperage going to be doing? Decreasing by the same amount. So it's down, by 1,000 times. And it's a set amperage. So what we've got now is 0.01 amp, which would be what, 10 milliamps, right? So, but we've got a set amperage. So what we need in our exposure is really three things. When we make an exposure, what are the three components of X-ray exposure? KVP, MA, and time, right? So at the same time, what we're going to have is a secondary circuit. That secondary circuit comes off in parallel to the primary circuit. And we've got an MA selector. An MA selector, after it goes through the MA selector and we select our amperage in anticipation of it becoming milliamperage, is that it goes through a reverse of this. So as we change in a step-up transformer, as a step up, it steps up the voltage. What we want to do is prevent electrons from jumping across the tube too early. All right? Voltage is that force that makes the electrons go. We don't want them to go across the tube until we're ready for them to. So we don't want kilovoltage until we make our exposure button. What we need is low voltage. So if that steps up voltage, and what I want before I make an exposure over here in the filament is actually maybe 15 to 25 volts, very low voltage. Then if this is the process of increasing voltage, what could we do to decrease voltage? Flip it around, right? So what we'll have in a step-down transformer, this is step-down transformer, is more turns on the primary side than what we have on the secondary side, and then we'll feed that into the filament. Okay? Now we have low voltage, and we have a set amperage, so that whenever we hit our prep button, what we're going to do is we're going to flood this thing with electrons to create a space charge. What else do we call space charge? Hot charged particles, emission of hot charged particles.
Electrons.
It's electrons, it's ions, so you're creeping up on it. Hot is heat, thermionic emissions. There we go. So we got thermionic emissions. So when we press our prep button, this isn't doing anything yet in the prep stage. This is activated so that we select our MA, we step down our voltage, and we heat up our filament to create thermionic emissions. All right? So we've created a space charge, a collection of electrons on the filament in anticipation of making an exposure. Now when we push the exposure switch, at the same time we'll get rotation of the anode. So that's all happening during prep stage. The only thing that happens during exposure stage is this becomes relatively much more positive and this becomes much more negative. And we'll make our exposure, these things jump across the tube. Okay? So, alternating current, gotta have it. Alternating current, gotta have it. Alternating current, it's there. We're gonna learn that by the time we get to this point, we don't want alternating current anymore. So that's really kind of in the next stage. But all the way up to this point right here, we have to have alternating current. All the way up to this point right here, we have to have alternating current. Why? Because alternating current creates a changing magnetic field, right? So that if we move a secondary coil close to it, we can induce, induce a alternating current in the secondary side, and we can increase or decrease the magnitude of the voltage in the secondary side. Okay? So why do we put an iron core in it? It's ferromagnetic to induce a magnetic field also in the ferromagnetic material to join the magnetic fields so that you get a stronger magnetic field. That's all it's for, is to just create a stronger magnetic field. Now, we're still going to have some problems with it. And we're still going to have some loss. Right? So I've been drawing this as if to say that if we plug in directly in the same spot on the opposite side of the magnetic field, then we're going to have exactly the same voltage, right? Right? That's what I've been telling you. I've been lying to you. It doesn't happen that way. All right? You're going to have some loss. You got loss for three different reasons. All right? One is that you've got resistance in the wire. Okay? So you send the electrons through the wire because they're rubbing and bumping up against each other and running up and down the wire, and you're going to have loss. It heats up, that creates more loss. So how do we deal with heat in the X-ray tube? Three different ways we talked about. The fan, that was the oil. Right, so we've got fan, oil, so we got, in those, we've got convection, convection's the fan. We got oil, which is conduction from the tube down into the oil, and then we've got thermal radiation from the anode and the cathode directly to the glass. So we've got three different ways to deal with it. We don't have all those to deal with here, but we can take these and put them in a great big box and fill them up with oil to try to keep them cool, and we do that. Okay, so each one of these are in its own oil bath. Maybe not this one, but this one absolutely has to be. Okay, so we got oil inside of it to reduce the resistance. Does it reduce all the resistance? Oh, did I call it a superconductor? No, even a superconductor still has resistance. It's just very low. That's not a superconductor, it's electromagnet. Electromagnets can be superconductors. That doesn't happen here, all right? That's MRI with liquid hydrogen, liquid helium, not hydrogen, liquid helium. We still have resistance, so we're going to lose some due to resistance. All right. Other things are that we've still got some of these little spinny magnetic fields around the wires themselves, and that's what we call eddy current. All right. So you ever stood on the bank of a flowing creek or a river, and maybe there's some branches down into the river, and you see the water going down and it hits the branches and it starts spinning? You ever seen that? That's what you call eddy current. That's all it is. The eddy current is just spinny little currents is all it is. And even though we put an iron core to reduce those, they're still present. They still happen. And the other is what we call hysteresis. Hysteresis. And hysteresis, you can look it up and it gets kind of complicated, but in effect what it is because electrons are going that way. Anybody ever played basketball? Okay, running the lines. You know what running the lines is, right? If you don't, then you've never played basketball or you've had a horrible coach. So running the lines, what you did was, there's lines on the floor of the gym, and what you have to do is you have to run out, bend down, touch one, run back, touch, run to the next line, touch, run back and touch, and so forth. So every time you change directions, are you going the same velocity at the beginning of each one of those? No. That's hysteresis, basically, an illustration of hysteresis. Since electrons are going in one direction, they got to slam on the brakes and go back in the opposite direction, you're going to have some loss. You're not going to have a constant 100% strong magnetic field at all times. It's going to increase, decrease, increase, decrease, even while it's flipping back and forth. Okay? So you got those three things. Those three things are still present. And we're gonna deal with them in different ways, you know. We added the core to reduce eddy currents. We added especially in the high voltage transformer, the oil to reduce just resistance in the wire, the heating of the wire. But back to these two, we can improve our efficiency in these things with different types of transformers. All right, so I'm gonna erase everything down to the high voltage, because this is really kind of where it applies most.
And you said you improved the efficiency by changing the transformers?
Yeah, we're gonna change the different core types. Okay. So what we have in hysteresis also is, because we've got a changing magnetic pole strength over here. I don't remember if I took it out of the notes or not, but it's out of the textbook for sure. But Lenz's law is another law that states that the magnetic field that's induced in the secondary side opposes the magnetic field that is created in the primary side. So that's a lot of words to say this. On your primary side, you apply alternating current and you get a changing magnetic field, right? But what's going to happen in the secondary side is that our magnetic field is going to be exactly the opposite. So it's going to be like that. All right, so again, hysteresis, we got hysteresis loss. So we got resistance there as well as the foundation for Lenz's law. All right, so what we can do to improve the efficiency is add the core, but in adding the core, again, what we've got are two separate and completely different magnets. What if we could join them up? Magnetic fields go out and in, right? And out and in. And this one's going out and in, and this one's going out and in. They're doing their own thing within the sphere of each other. But what if we joined them up? What if we took and joined these two up at the bottom? Okay, so now our ferromagnetic material is shared between the two, and we've got a common link going in between both of them. So if we've got a common link going in between both of them, does that not give the magnetic field lines an easier place to go? It's coming out of the bottom of this one and going into the top of that one, which is still, we've still got the same problem with, you know, switching pole strengths, but does it not give the magnetic field a place to go? Sure it does, right? So this is what we call a closed core transformer. Closed core transformer uses basically a connection at the top and the bottom of two open core transformers to improve the efficiency and give the electricity, or give the magnetism a place to go, so that it takes it directly out of one and jams it directly into the next one. All right? So open core would be just that, what I initially drew. But still, even here, what we've got are magnetic fields that are, yeah, we've got a pathway for them to go and a closed loop of magnetism right there in the middle, but we're still wasting some. So what somebody else came along and did was they took and built on that, and they said, okay, what if we take two coils of wire, we wrap both coils of wire around the same middle piece. Now our magnetism is going to come out, and it's got a 360 degree, or close to it, avenue of ferromagnetic material to travel through in order to ram that magnetic field up and down through both coils. Does that kind of make sense? So magnetic fields, because they reach out in both directions, or really all directions, if we take our ferromagnetic material and we make it to where the magnetism can travel through in all directions, and then go right back up through the same magnetic field, then we strengthen and we don't lose any magnetism out here, or as much magnetism out there. That's what we call shell type. The shell type transformer is what most of your equipment's gonna, where your step-up transformers are gonna be in most of your equipment now. Yeah.
I have a question real quick, going back to the other one where it has the south and north poles.
Mhm.
Would the opposite one, since they're attracted, would it be north, like a south?
I'm sorry?
Is at the top on the other one?
Oh, yeah, it'd be, it's coming out of one, going into the other, coming out of one, going into the other, so they're still, yeah, they're still opposites. Yeah. Now, if you're gonna ask me here if they're opposite, I can't tell you, I don't know, I really can't say. I would think no, because then you'd have magnetic fields bumping into each other right in the middle. But honestly, I've not done the research, that just came to mind a second ago. I thought somebody's gonna ask me that, I could get in front of this and say, I have no idea. So, but shell type's most efficient, and what you may read in the textbook is that what they'll do is it's not just a single piece of metal, but it's what they call a laminated core. And a laminated core, for whatever reason, helps with eddy currents. And you know what plywood is, right? If you look at the edge of a piece of plywood, plywood is laminated. So you got a good piece of wood on the front, a not so good piece of wood in the back, and scraps in between. That's lamination, essentially. And again, I'm not real sure how it is laminated cores are more helpful to get rid of some of those eddy currents. They just do. Okay. So most of your machines now are going to use shell type with a laminated core to reduce loss. So are they still, you know, do we still have loss? Yes. So are they 100% efficient? No, but they're close enough that we can say that, you know, they're extremely efficient. And part of the reason they're so efficient is because there are no moving parts there. Anytime you introduce any kind of mechanical energy into electromagnetic devices or electromechanical devices, you're going to have a tremendous amount of loss. You know, it's some of the power is going to go into just creating that mechanical energy. And since there's no moving parts here, they may be 99.5% efficient, very, very efficient. But they're still not totally efficient. So back to our auto transformer, what we may have is we got, and this is not on the test, it's just bonus material. So what you may have is contacts on the primary side there with contacts on the secondary side there. Right, spread out just a smidge to compensate for the loss due to those three things: the eddy currents, the hysteresis, the resistance in the wire. Okay, so how do they work? Well, you know, like that, but there is mathematics to it, and that is according to the transformer law. All of our transformers work according to the transformer law, and transformer law says two things. And that is the change in voltage between the primary side and the secondary side is directly proportional to the change in turns ratio. And a ratio, you know, like grid ratio is 8:1. That would be, you know, specific things compared to specific things. In a step-up transformer, what you may have is 1 to 1,000. So what we have in transformer law is, if you flip over to page 80, you'll see two different things. So transformer law, the first one says voltage on the secondary side over, and that's what the S stands for, on the secondary side, voltage on the primary side is equal to N represents the number of turns, right? It's number of turns on the secondary side over number of turns on the primary side. So voltage on the secondary side over voltage on the primary side is equal to number of turns on the secondary side over number of turns on the primary side. I kind of changed We'll do it like that, okay? So it's directly proportional. 2, 2, 1, 1. Voltage is directly proportional to the number of turns. So what we have is, let's say we've got our voltage on the primary side is 100 volts, okay? Our number of turns on the primary side, we're gonna keep it simple, is 1 volt. Our number of turns on the secondary side is 1,000. So what is our voltage on the secondary side? If we set it up, that would look like X over, because we don't know, 100. We know what our primary voltage is equal to 1,000 turns on the secondary side over 1 turn on the primary side. So how do we solve that? Cross multiply, right? So 1 times X is equal to X. 100 times 1,000 gives us 100,000. Okay, so our voltage increases, but looking at the second part of that, the effects on current. Notice this. Intensity is current, right? Intensity is current, current is amperage, amperage is number of electrons. Intensity on the secondary side over intensity on the primary side is equal to number of turns on the, what does it say? Your eyes better than mine, I know. Primary side over number of turns on the secondary side. So intensity on the secondary side over intensity on the primary side is equal to number of turns on the primary side over number of turns on the secondary side. Okay? So as voltage goes up, what does that say about amperage? What's going to happen to amperage? It's going to go down, right? Secondary, primary, secondary. Yeah. So let's do this. So we've got, let's say, 10 amps on the primary side. We don't know what we're going to have on the secondary side. Now we're going to go to our step down, maybe. So step down, we've got 10 amps, and then we've got, let's see, number of turns on the primary side, we'll say is 100. Number of turns on the secondary side is, we'll say is 10. So how do we work this? Again, we're going to cross multiply, so we got 10x is equal to 1,000, right? So x is equal to, what did I do wrong? Oh. Is that what I did wrong? X is equal to 100. I did something drastically wrong. So what I should have, number of turns on the secondary side. Intensity on the secondary side, intensity on the secondary side. I did something wrong. I'll work through this. But it should decrease. So number of turns on the primary side, I'm going to have more turns on the primary side than what I have on the secondary side. There we go. No, that's exactly how it's set up. Less turns on the secondary side. Yeah.
On the primary side. Secondary side, you'll have more turns, right?
That would be a step up. Step down, I'm going to have more turns on the primary side. Primary side, more turns. Yeah. What am I doing wrong here? Intensity. Okay. No, I'm not going to stand up here until I figure out exactly what I'm doing wrong, but a step down step down transformer is going to step down voltage. I'm working amperage. That was right. So instead of doing that, let's go back to our illustration there. Okay. So our voltage increased, our amperage should decrease. So I've got intensity is equal to X. I'm still kind of running into the same thing. 10 amps is equal to number of turns on the primary side. So yeah, I was working step down transformer. Number of turns on the primary side, again, you were right. Our number of turns on the primary side, what would we say? It was 100. Number of turns on the secondary side was 1,000. So, feed at 10 amps, I've got 1,000 X is equal to 1,000, so X is equal to 1. So in a step-up transformer, what we're gonna have is an increase in voltage and a decrease in amperage, okay? So what I was doing there was, I went from a step-up transformer, which should have step-down amperage, to a step-down transformer, which is gonna increase amperage. So, I changed my perspective. So in the step-up transformer, what we're gonna have is a change in voltage on a order of 1,000 times. And what we're gonna have, increase in voltage by 1,000 times. What we're gonna have on the amperage is a decrease by the same percentage, same amount. Okay? So transformer law. Voltage increases on a step-up transformer, amperage decreases on a step-up transformer. Step-down transformer, voltage decreases, amperage increases. Okay? So, any questions?
So it's safe to say that voltage and amperage are always gonna be
Inversely
inversely
proportional.
proportional?
Yeah, yeah, yep. The only example where that might not hold true would be as if you changed your resistance to compensate for one or the other. So, you know, if your ohms remain the same, then they're gonna be inversely proportional. All right. Any other questions? Okay, so to make a schedule where we could have a test, you know, combine both portions of chapter 4 into a single test, but also did something else. I'm going to give you a take-home portion. So the test questions between the two tests, previous tests, there was a lot of redundancy. So what I tried to do is go through both tests and combine, or not combine, but separate the redundancy in two separate portions and give you one as a take-home portion that should help as a study tool. All right. You're not going to have the same questions on the test next week or on Friday is what I'm sending you home, but this should help you to prepare for the test. So what you're going to do is when you come back Friday, you're going to bring this back with you, and for the students who are not here today, I'll post it on the in Canvas so that they can have it as well. But what you're going to do is you're going to bring this back, or you don't have, bring this back, but also bring me back a Scantron with your answers for this test, plus bring a Scantron for Friday's test as well. What I'm going to do is I'm going to grade both of them, and since this is, you know, essentially an open book test, it's not going to count as much as the test on Friday, but it's still going to count. So what I'm going to do is the test, the in-class test on Friday is going to count 75% of this particular test grade. This is going to count 25%. Okay? If you don't bring it back, then your test grade on Friday just stands as is. But I'm not going to take them late, so make sure you bring it back on Friday. Okay?
So you want the test and the
Yeah,
Scantron back?
test and Scantron back. Yep.
Oh, that one's-
Yeah. Mhm.
The formula on the right is still sucks, and the one on the left is different.
No. Those are both step up. It's just that the voltage increases and the amperage decreases in a step up transformer. In a step down transformer, the voltage decreases and the amperage increases.
So you said this is kind of like a study material as far as the test in general, or just a portion of it? Or just?
Yeah. You know, after I separated them, I really didn't go through and analyze if everything was on there.
Okay.
It should help you with a portion of it. Certainly study your notes and go back and, you know, look over the videos and whatnot.
Okay. Awesome, thank you.
All right, then I'll see y'all Friday.